All right, guys, so now let's take a look at a basic acid-base problem. And usually in these types of problems, they like us to calculate pH. So let's see what our next problem entails. Over here, they're asking us to calculate the pH of a 0.50 molar hydrocyanic acid with an acid dissociation constant of 6.2 times 10 to the negative 10. So this is about as typical as a problem of this type is going to get. Yeah, you really need to know how to master this type of a problem. A second portion of the question is asking us what is the pH of a 0.24 molar solution of potassium cyanide. So we'll get to that. Let's take a look at the first part of the problem first. And what should jump out at us over here, the fact that they're asking us about pH, the fact that they're giving us an acid dissociation or a Ka constant, all of these things point to having to make an ice table. So let's get on that. Now remember, we're making an ice table and it's an acid that we're dealing with, and so we should know the basic format of how an acid dissociates. The idea is that if you have some sort of an acid and you mix it into water, of course water is always liquid, it is going to give us a protonated hydrogen or an H plus ion plus A minus. Now some of you guys may have seen instead of H plus, H3O plus. Those are the same for all intents and purposes. So in order to make an ice table, let's go fetch one, because that's what we're going to have to do here. So here's our ice table. And let's break up our acid. So we have hydrocyanic acid, to which we're going to add water, and it's going to give us H plus and A minus. Now this guy, the water, the fact that it's liquid, is often omitted from this equation, so you may not want to write it, and that'll be acceptable. This entire column, as you should know, does not matter to us. So let's take a look at what we have initially. It's also a good idea. We know that we can make ice tables for using different units. We can do this in moles, in pressure, in concentration, in molarity. So I like to, just mention in the top left corner the units that I'm using over here, and our units are going to be molarity, capital M. So if we read the question, we realize that we have a 0.05 molar solution of hydrocyanic acid. So we're going to insert that value as our initial value. And of course, no products have been formed yet, so those are going to be 0. Now, in order to reach equilibrium, some sort of a change is going to take place, and in this case, it is not difficult to realize that the equation is going to move to the right. Some of this guy is going to get used up, and exactly the same amount of these guys are going to be created. Now remember that these x values follow the stoichiometric coefficients that are over here. So if this was a 2, for example, this would have been plus 2x, right? The ratio stays intact, and at the end of the day, we are left with 0.50 minus x over here, and x over here, and this is our equilibrium condition. At this stage, we can actually write out our expression for the acid dissociation constant. We've practiced this a number of times, so we should be fairly fluent in knowing how that's going to work out. So over here, in our case, the equation essentially always takes on this format. So let's write the general form here first and then apply it. So this is what our equilibrium expression is going to look like. Filling in the values that we have is going to allow us to solve for x. Now we know that the Ka value given is 6.2 times 10 to the negative 10. The fact that this value is such a small number tells us that this acid dissociates very little. Okay, it doesn't move to the right too much. The larger the K value, the higher the dissociation. So we have x times x all over 0.5 minus x. So at this stage, what we could do is think about the problem a little bit and see whether it is worth making an approximation. Generally speaking, if the dissociation constant is small compared to the initial condition, which in this case it is. Now, different teachers teach this different ways. Some say 100 times smaller, some say 1,000 times smaller, but for us it doesn't really matter. It is way more than 1,000,000 times smaller. It's 10 to the negative 10. So no matter what method your teacher likes to use, for sure over here we can expect our x to be small, and therefore we can approximate this to be just 0.5, and that'll prevent us from having to necessarily use a quadratic. So we're going to assume that x is small. Now, if we assume that x is small, then 0.5 minus x is approximately just 0.5. It's like me giving you $1,000 and taking a penny back from you. Applying this approximation simplifies the math quite a bit, because this is what we are left with, and it's not going to take us long to figure out what x is equal to. So we're going to take 6.2 times 10 to the negative 10, multiply that by 0.5, get an answer of 3.1 times 10 to the negative 10, and then finally take the square root of our answer, and we're going to discover that x is equal to 1.76, let's keep some decimals over here, times 10 to the negative 5. And of course, this is a concentration. Once we have this, we need to realize that our x value is the amount that this guy has dissociated. We can see that it is very small compared to the original. In fact, we need to do that regardless to make sure that our assumption is actually valid. In order to check whether your assumption is valid, what you want to do over here is take your answer, divide it by the initial concentration, and multiply it by 100 to see the percentage of x versus the initial concentration. As long as that percentage is less than, once again, depending on the teacher, some say 1%, some allow for 5%. As long as it's a small percentage, you should be okay, and you can say that your approximation was in fact valid. So if I carry out this calculation, if I divide my answer by 0.5 and multiply by 100, we see that this is equal to 0.0035%. So this is less than even 1%. That's about as low as your teacher is going to go. So since it is less than 1%, we can say that the approximation that we had over here is a valid one, and we can proceed. Now, the next thing we want to do is recognize the fact that x also represents the equilibrium amount of H+. We know now that the concentration of H+ at equilibrium is also going to be equal to x, or that amount. And that is what we need in order to calculate the pH. So we're almost there. We should understand that the pH is calculated as negative log of the concentration of H+ ions. Applying this formula is going to allow us to answer the question. So negative log of 1.7607 times 10 to the negative 5. So let's do that. Negative log of 1.7607 to the power of negative 5 gives us a pH of 4.7543. And now we should take a look at our significant figures to make sure we have the appropriate amount. In our calculation, we are given 2 sig figs over here. We're not doing any kind of addition or subtraction, so we should be okay. We should write our answer to 2 sig figs, or 4.8, and that'll be our pH value. Now, we did all of this work. We made our ice table, we made our approximation, and we applied the equilibrium expression and this formula to calculate the pH. It turns out that if you have a weak acid where your K value is small, okay, where the approximation is valid, we can apply a nice little trick over here to get to this solution in a much more efficient fashion. So let's take a look at another way of solving this problem using a little trick that I'm going to show you. So it turns out that these are 2 formulas that you may not be familiar with, but you can apply to problems like the ones we've just done, weak acid dissociations essentially, that you can use an approximation in and get to our answer much quicker. So if we know this formula, then we can get till here without doing any of the work we did with the ice table. All we need really are the 2 values given in the problem, the concentration and the value of Ka. Take a look at what I am saying. If we apply this formula over here, we can obtain the concentration of H+ ions, which is what we need to calculate the pH, immediately. Our K value was 6.2 times 10 to the negative 10, and our HA value was 0.50. Let's take a look at what this gives us if we were to actually calculate it. And you will notice that it, of course, will give the exact same, that was a 7 at the end rounded. It's going to give us the exact same value that we got over here. Take a look at how quick that was. Once you have that, you can calculate the pH like we did over here and get to the answer in under 30 seconds. It requires that you memorize that formula. Now, if your approximation was not valid, because you obviously have to check, that means you have to use the quadratic. And even there, you can save yourself some time because your quadratic will always take on this format over here. So you can skip a few steps and get to the answer much quicker by applying these formulas. This being said, though, you got to be careful about who your teacher is. There are certain teachers that will not accept these, but recently in exams they like to ask these questions as multiple choice questions, and in a scenario like that, this can be extremely helpful. Let's take a look at our second part of the question next. So in the second part of the question, they're asking us to find the pH of a 0.24 molar solution of potassium cyanide. Now, it is good that we did the first part of the question first, rather than doing this one right off the bat, because this teaches us something. Over here, if we were to create potassium cyanide, KCN, now if you came to the tutorial and studied last week, you would know how to recognize this guy to be a spectator ion right off the bat. Right off the bat. We know how to quickly figure out what spectator ions are, and that would eliminate this guy for you and make you focus only on the Cn negative ion. But even if you didn't know that, the first part of the question is a nice little clue for this second part. This second portion shows you Cn as being the conjugate base of HCN. So you know this guy, as opposed to the previous one, is a basic. It's going to be a basic problem. So a conjugate base, so since this guy is a conjugate base, in order to solve the same exact problem, remember the first thing we're going to do is not use the Ka value, but rather the Kb value to get the job done. And we can make an exact same ice table as we did previously. We should know how to take a base and break it down. However, over here, we're going to apply our little trick in order to save some time. Now, the same exact trick, the same exact formula can be manipulated a little bit to give us the concentration of OH minus ions. So the concentration of OH minus ions, this exact same formula for a base would be Kb, the concentration of A minus. Applying this formula will give us OH, using which we can calculate the pOH and therefore the pH. Let's take a look. Oh, where did it go? There it is. So let's apply this formula, and it's going to give us OH minus is equal to Kb. Now to calculate Kb, remember you can use Ka to calculate Kb. You take 1 times 10 to the negative 14, which is Kw for water, divided by your Ka, 6.2 times 10 to the negative 10, and multiply this by your initial concentration, which in our case is 0.24. Applying this formula is going to give us OH. So I get an answer equal to 1.9675 times 10 to the negative 3. And the rest of the procedure should be fairly straightforward, guys. We're going to calculate pOH by taking the negative log of our answer. Giving us 2.7. And then finally, our pH is equal to 14 minus our pOH. Or in our case, a pH of 11.3, which again, if it is, again, 2 sig figs, you want to leave that to 11. And that makes sense. Our pH is over 7. That makes sense for a base. So hopefully that was helpful, guys. Understand this little trick. It'll save us a lot of time. And at home, you guys should practice this problem once again by building an ice table for a base. All right, let's move on to our next problem.